A Bifilar coil is simply a coil wound with two wires side by side instead of one. A bifilar coil is simply a coil wound with two wires side by side instead of one. Tesla's version was patented as U.S. Patent 52340. Coil for electromagnets, filed July 7, 1893, and patented Jan 9, 1894. His main idea was not free energy, but a coil with extra built-in capacitance between adjacent conductors, so the coil could partly neutralize its own self-induction and resonate without as much external capacitance. How it is assembled: the Tesla-style flat, pancake bifilar coil. Take two insulated copper wires, preferably magnet wire of two colors. Wind them together side by side in a flat spiral, like a snail shell. You now have four ends: A1, A2, B1, B2. For Tesla's series connected bifilar, connect the outer end of wire A to the inner end of wire B. The remaining two ends become the coil terminals. That makes adjacent turns sit at a larger voltage difference than in an ordinary single-wire coil, giving much higher distributed capacitance. Modern studies confirm bifilar coils can have greater self-capacitance and lower self-resonant frequency than conventional coils of similar geometry. Main types. There are several different bifilar arrangements. Tesla series bifilar. High self-capacitance, lower resonant frequency, useful for resonance experiments. Parallel bifilar. Lower resistance, more current handling. Counter-wound bifilar. Currents oppose, magnetic fields cancel. Used for low-inductance resistors and shunts. Common mode choke bifilar. Two lines wound together on a ferrite core. Blocks noise common to both wires while passing useful signal. Bifilar common mode chokes are common in data, sensor, USB, HDMI, and RF filtering applications. Practical uses. Real, proven uses include wireless power transfer and resonant coils. Bifilar self-resonant coils can reduce or eliminate some external capacitors in tuned wireless power systems. Noise filters. Used in common mode chokes for electronics, radio, data lines, and power line interference. Non-inductive resistors. A folded bifilar winding makes current go out and back beside itself, canceling magnetism and reducing inductance. Tesla-coil experiments, especially pancake coils for high-voltage, high-frequency resonance. Sensors and pulse coils. Because the geometry changes capacitance, inductance, and field distribution, it can be useful in experimental magnetic pickup coils, pulse systems, metal detection, and RF work. Could it reduce energy expenditure? Yes, but in a normal engineering way, not by creating free power. A bifilar coil can improve efficiency by better tuning. A resonant circuit wastes less energy when driven at the correct frequency. Less external capacitance. Tesla's idea can reduce the need for separate capacitors in some designs. Lower noise losses. Common mode chokes can reduce RF noise and wasted interference. Improved wireless coupling. A self-resonant bifilar coil may transfer power efficiently over short distances, but it will not produce more energy than is put in. Any overunity or free energy claim should be tested with input/output meters, heating losses, and battery isolation. Best practical experiment for your lab. Build a small flat Tesla bifilar coil. Use 2226 AWG magnet wire, two colors, 50, 150 turns, flat plastic or wood base, no metal core. Measure it with an LCR meter, then compare it to a normal single-wire pancake coil of the same size. Look at voltage rise at resonance, resonant frequency, current draw, heating, magnetic pickup, and wireless LED lighting distance. The most promising practical direction for Global Robotics lab use would be self-resonant wireless charging pads, RF filtering, sensor coils, and low-loss tuned power circuits. Global Robotics Corporation, Robert Coley.